Statsproblems.com was used to create this tutorial, which can help us calculate an independent measure's ANOVA with equal number of scores in each group, but with less calculation than a complete test because the means and variances of all the groups are given. Let's begin by selecting one of the 25 example problems. The question appears in the blue box. A set of population scores is normally distributed. Sample information from 3 unrelated groups appears below. For Group 1, mean x bar 1 equals 25. Variance S1 squared equals 44. Number of scores N1 equals 7. For Group 2, mean x bar 2 equals 15. Variance S2 squared equals 48. Number of scores N2 equals 7. For Group 3, mean x bar 3 equals 5. Variance S3 squared equals 43. Number of scores N3 equals 7. Alpha is 0.05. What are the results of the hypothesis test comparing the sample means of the 3 groups to each other? Let's step through the solution by clicking on the Next Step button. In Step 1, we calculate the grand mean x bar g. X bar g is equal to the sum of the 3 means, x bar 1 plus x bar 2 plus x bar 3, divided by the number of groups, k. In this example, x bar g equals 25 plus 15 plus 5, divided by 3, which works out to 45 divided by 3, which works out to 15. In Step 2, we calculate the mean square within groups, ms, within groups. Where k is the number of groups and j is a particular group in a summation series, the mean square within groups, ms within groups, is equal to the summation of the variance for all groups, divided by the number of groups, k. In this example, ms within groups equals the sum of Group 1 variance, s1 squared, plus Group 2 variance, s2 squared, plus Group 3 variance, s3 squared, divided by 3. With these data, ms within groups equals 44 plus 48 plus 43, divided by 3, which works out to 135 divided by 3, which works out to 45. In Step 3, we calculate the mean square between groups, ms, between groups. Where k is the number of groups, j is a particular group in a summation series, x bar g is the grand mean, and n is the number of scores in each group, the mean square between groups, ms between groups, is equal to the number of scores in each group, n, times the summation of the difference between each group mean, x bar j, and the grand mean, x bar g, squared, divided by the number of groups, k, minus 1. In this example, ms between groups is equal to 7 times 25 minus 15 squared, plus 15 minus 15 squared, plus 5 minus 15 squared, divided by 3 minus 1, which works out to 7 times 10 squared plus 0 squared plus minus 10 squared, divided by 2, which works out to 7 times 100 plus 0 plus 100, divided by 2, which works out to 7 times 200 divided by 2, which works out to 7 times 100, which works out to 700. In Step 4, we calculate the observed f value. The observed f value, f, is equal to the mean square between groups, ms between groups, divided by the mean square within groups, ms within groups. In this example, f equals 700 divided by 45, which works out to 15.556. In Step 5, we calculate degrees of freedom. The degrees of freedom within groups, df within groups, equals the number of scores in each group, n, minus 1 times the number of groups, k. In this example, df within groups equals 7 minus 1 times 3, which works out to 6 times 3, which works out to 18. The degrees of freedom between groups, df between groups, equals the number of groups, k, minus 1. In this example, df between groups equals 3 minus 1, which works out to 2. In step 6, we find the critical F value. We need the alpha level and degrees of freedom to look up F critical value. The alpha level is 0.05, the degrees of freedom between groups is 2 and the degrees of freedom within groups is 18. In the F table of critical values, the column of the table indicates the numerator of the F ratio, which is the between groups degrees of freedom for this analysis. The row of the table indicates the denominator of the F ratio, which is the within group degrees of freedom for this analysis. Use interactive table 8 to find the critical F value. Using the alpha equals 0.05 table, with df numerator of 2, df between groups, and df denominator of 18, df within groups, to find the critical F value of 3.55. We close this window to return to the analysis, which shows that the critical value from the table with df numerator between groups equals 2 and df denominator within groups equals 18 is 3.55. In step 7, we test the hypothesis. The observed F value of 15.556 is greater than or equal to the critical F value of 3.55, so we reject the null hypothesis. In addition to the 25 example problems, we can work step by step through an unlimited number of new problems using the Generate button. The Edit Data button can help us create problems with customized input. Instructors can use this function to create problems with complete solutions to use on exams, in class, or for homework. For printed output, we can print the question. Or we can print the question with the complete solution. You can also work out the complete independent measures ANOVA with scores as input, but this problem solver takes a long time to work out with so many steps. The free website has statistical analyses in all of the most common areas in statistics. Statsproblems.com also has a mobile version so you can access the site from anywhere. For help with statistical concepts, HelpMeWithStats.com is a free website that has more than 70 tutorials, as videos, or as self-paced slideshows. In addition, HelpMeWithStats.com gives you free access to a comprehensive stats textbook with more than 685 review questions. Thanks for watching. If you find these resources valuable, please share statsproblems.com and HelpMeWithStats.com with your friends and instructors.